expression that the mathematician is now ready for dinner, right? So, and then you look at it and say, okay, I'm an engineer, I want to see more. So we do the same thing. We ask, for any of these x elements, now I pick x11, okay, in feature map 0, channel 0, or input feature map 0, x11. I ask, what's the importance of x11 to the output element, right? Because I already have the importance of the output element to the error, so I need to now ask how important is each x to the output element, to each output element, right? And then I have the chain rule, right? Once I have the whole chain rule. So the way to see it is that what are the things that can contribute to the error? x0, let's say x11 can contribute to y11 by multiplying with the w00. So this is just the convolution. If you go back, you look at how that x11 is affecting y11, you see that it's multiplying with the upper left corner, okay, upper left corner of that filter. So x11 contributes to y11 through w00. But x11 can also affect another y element, which is the y0 by multiplying w01, because basically x11 will also affect the next another y value by when you do the shifting of the convolution to the right, and then you would affect y10. And then you will affect y01 with the shifted w the index and so on. But in general, there are not that many of these terms, because each x value is going to only affect a limited number of y values. The scope is defined by that filter. The bigger the filter, the more y values each x value affects. Right? So that's why, in general, the total number of terms in this kind of thing is only k by k. Okay, smaller. 3 by 3, you only have 9 terms, rather than potentially millions of terms in the previous example. So, if I calculate delta E delta x, okay, for input element 0, channel 0, element 1, 1, I'm going to do the chain rule again. I'm going to take, take the delta E delta y 1, 1, okay? And then, it will be timed delta y 1, 1 and delta x 1, 1. And this term, I know exactly here, is w00. Right? Because this is how x11 feeds into y11. And so when I do the differentiation, x goes away, I have w00, right? Just like last time. But now it's w, not x anymore, because we're finding the importance of x. When we do a differentiation, x goes away, and the w is a constant now. Right? So w remains here. And then we can also tell that wx will affect y10, and the way that it affects 10 is by multiplying with w01 here. So I'll take the delta E delta y10 and multiply by w01, right? So these are the terms that I'm going to see as far as how the x11 in input feature map 0 is going to affect the error. I'm going to have k times k terms here, okay, so that I can generate the value, right? So if I look at it, it's actually also a convolution pattern, but it's actually a kind of it's transpose convolution. Meaning that instead of having exactly identical indices multiplied together, it's the index that add into 1, 1, right? So, the upper left corner is going to be adding to the lower right corner, right? The multiplication is going to happen between a kind of a mirror image of the matrix. So it's a transpose. If you transpose this matrix, the W matrix, then it becomes a real convolution. Does that make sense? Right? Because if you transpose this, 0, 0 becomes 1, 1, and 0, 1 becomes 1, 0. So then you have identical index multiplication. That's the real convolution. So this is why we call it a transpose convolution. We take the filter, if we do the transpose of that filter, it becomes a real convolution. But the convolution here is really just the complement or the transpose form. So you can write the same piece of code, but with the indices, and then you can just write the code this way, and then it will calculate sequentially the matrix, all the delta E, delta X, and if you look at how it looks like, remember, in order to calculate, this is what we're trying to calculate, delta E, delta X. And there will be multiple input channels, right, to calculate. And so we're going to take delta E, delta Y, and go through the W matrices, right? You can pick up the W matrices in the convolution part, right? That convolution, actually transpose convolution, and then generate each of these elements, right? As soon as you hear that, you know exactly how to implement this with matrix multiplication, right? You treat this thing, the delta E, delta Y, as the input matrix, right? As the input matrix. You transpose the W matrices and treat them as the filter matrices. Then you know how to, you already know how to assemble the matrix multiplication input on both sides, right? We already talked about that. And this is actually quite close to the forward inference because the filters are of exactly the same dimension. So the dimensionality-wise, it's going to be very similar to the forward. It's just that you need to transpose the weights, right? And that's it. Okay. So I eliminated quite a few slides because we used to go through another level of examples. But I believe this is actually a little bit more intuitive, and also because of fewer steps, it's less likely you get lost in the middle. Okay? Does that make sense?
Yes.
Okay, very good. Very good. So we're done here. So I don't think we need to go through any of these examples anymore because you're already there. So if you're interested, you can actually take the training process, training process as your final project if you want, if you're interested in this domain. And there are multiple optimizations that you can play with, right? You probably you can already start to smell some of these optimizations, right? How do you do the transpose quickly? How do you, dynamic, you may not even need to do the transpose. You can actually just, when you fetch the tiles, right, into the registers or the, shared memory, you can realize the transposition, but you need to fetch them in a coalesced way, right? And if you have, very large, let's say if you have very large matrices, you may want to do the multi-GPU version, right? So then, how do you partition your matrix into multi-GPU? So basically, you need to think about how to do a multi-GPU matrix, let's say multiplication implementation, and it may be even better to try to, instead of partition the final matrices, you maybe better to partition the the input matrices and then do the matrix assembly, right? So there are all kinds of things that you can think about in terms of these calculations, and also when you calculate these gradients, and so one of the things that people worry about is that you may not have a big enough matrix to be able to spread across the multiple GPUs. So if you have smaller models, then there may not be enough the work for the GPUs. So people worry about doing mini batches, right, in different GPUs, and then they try to do the gradient, sort of the adjustment of the weights by exchanging the gradients, and then everyone will adjust the weights in a consistent way. And that's called a gradient exchange, and that's usually the kind of the bottleneck for multi-GPU training of the smaller models, right? So if you're interested, there are quite a few things that Carl and I can help you to look into as a project. But that's just one of the potential projects. So this semester, what we'd like to do is to give you some choices of maybe 3 or 4 possible projects, and then you can take on the project. In the past, we also we also let you do some take some of your research, and then you can use this opportunity to implement your research code in GPUs, and then try to get benefit. But I understand that many of you are MN students. You're not necessarily doing research. You're not necessarily trying to optimize some kind of existing research code. So that's why we decided to give you these 3 or 4 possible projects that make it life easier, okay, for you to do. But if you're a PhD student who really want to take on a research project and say, okay, I have some kind of research code that I would like to optimize for GPU, come and talk to us. Okay, the door is not closed, right? So we'll be happy to talk to you about whether or not if you're going to get somewhere with the optimization, whether the code looks promising, and whether or not it's going to be substantial enough for your a final project as well. Okay? Any questions? If not, I'll see you on Thursday. Oh yeah. No.
Can you talk about more about the pre-selected assignments for the
program? Thursday. Yeah, that's the Thursday. We're going to have a kickoff meeting. But so I'm just using this to lead into that because this is one of the possible projects. Okay, good.